So while up to this point we've only been dealing with uniform motion graphs, these aren't that common. So now we're going to start looking at non-uniform motion graphs, frankly, more realistic motion graphs, specifically V versus T graphs. And we're also going to introduce an extremely important concept, acceleration. See, uniform motion graphs will only have segments of motion with constant velocity. So looking here, the velocity is at 0.5 meters per second for 2 seconds, then 0, then 1 meter per second, then goes all the way down to -2. But that's not very realistic, because if you're moving, is it possible to instantly go from like 0 to 60 miles per hour? No. You have to steadily move to that velocity. And same thing here, we should never be instantaneously jumping between velocity values. A more realistic graph will look something like this, where we go, and then it starts to dip down, and then it starts to go back up to reach this velocity, and then it goes down a lot to reach this final one. Now, I want to be real clear, an even more realistic graph would be kind of curved at all these points rather than so sharp. But the thing is, though, is that even these sharp transitions are more realistic than what we've been analyzing up to this point. So let's go ahead and remove this uniform graph, and let's start looking at what we would call a non-uniform V versus T graph. Well, if we look, we have a bunch of different, let's see, 1, 2, 3, 4, 5, 6, 7 different segments. And let's look at these a little individually and figure out what they're really telling us. Well, we already know what all of these flat segments mean. If a segment is flat on a V versus T graph, remember you should always check what's on this axis first. If we have a flat segment, that means the velocity is not changing. So therefore, in those segments, we're traveling at some constant velocity, whatever that velocity may be. Now, though, let's look at, I'm going to skip to this segment right here. Well, if I look at this, initially, it has a velocity of 0, but then the velocity goes up to 1 meter per second. So what is happening here is that the object is at rest and speeds up to 1 meter per second. So it is speeding up. Was there any other place on this graph where something is speeding up? Because if we look, this is actually the only segment with a positive slope. So do we have another segment of the graph that is speeding up? Well, actually we do. And that's because if I look over here at this segment, I am once again starting at 0 and then moving to -2 meters per second. And you might go, wait a second, Mr. Varvier, that is a negative sign. But remember, the negative is simply telling you which direction you're moving in. It could be speeding up backwards. It could be speeding up to the left. It could be speeding up down. We don't know what positive and negative is here, but we know for a fact it's going from 0 to some greater magnitude value. Therefore, these two regions are speeding up. Well, now let's look at this region here. We start at a higher velocity, 0.5 meters per second, and we go to 0. And similarly here, we go from 1 meter per second to 0. So this chunk here and this chunk, just this part here, are both slowing down. So this is what we really want to get here. So a couple things we want to make sure we note. That if V is, the velocity is moving away from 0, that means we are speeding, there we go, speeding up. If V is moving toward 0, we are slowing down. It does not matter if we are moving toward or away from 0 on the positive side of the axis or the negative side. If we are going away from the axis, we're speeding up. If we're going towards the axis, we're slowing down. But one other thing I want to get here. What is happening when it is on this axis, which happens at 2 different points? Well, first off, we can see here we have a constant velocity of 0. So this means right in this segment, the object is just stopped. It's not moving. But what about this one? This is a little more bizarre because it says we're slowing down, and then it says we're speeding up. And additionally, at this one point, the velocity is 0 for an instant. But what exactly is happening here? And what is happening is that at this point, we are stopping for an instant to change direction. If I am reversing, so if I go forward here, actually, let me do side to side. If I'm going and then I go backwards, I can only go forward and backwards after I stop for an instant. I slow down and then speed up the other way. I can't just magically be going the other way instantaneously. There has to be at least a brief moment of rest. When I say an instant, I mean the tiniest fraction amount of time of rest. So if we cross the axis, so V crosses axis, this means stop for an instant and reverse direction. Whether that is going backwards or forwards depends on the situation. So let's have a brief return to velocity versus time graphs. Now, if we have a velocity versus time graph here, a couple things we want to note. One, we already have talked about this, and this is no different. Our y-intercept is going to be our initial velocity, how fast we are going at the instant that motion starts, or let me be real clear, it's really the first instant the motion is being recorded. It's possible the object was already moving, but we start our timer at this instant in time. So that's what the y-intercept is. But if I'm going to try to figure out what else I can get from this line, because previously we've always had flat v versus t lines, so what is this slope going to be? So let me pick this point here and this point here. So this would be what? T1, phi1, and this would be T2, phi2. And if I wanted to find the slope, I would do rise over run, and that would give me v2 minus v1 over t2 minus t1. Or if I want to rewrite this, I can say this is delta v over delta t. And we have a very specific name for this, because we abbreviate it, as I mess that up, with a lowercase, has to be lowercase, a, and this is the acceleration. So the slope of a v versus t graph gives ACC, gives acceleration. Now, a couple additional things I want to note here is if I'm going to write the equation for this line, remember we have to plug in the appropriate values. So instead of y and x, I have v and t. My slope is going to be the acceleration, and my y-intercept is going to be the initial velocity. So what is acceleration exactly? And most of you probably have an idea, because when you say that something accelerates, we say, oh, it's speeding up. And that's pretty close. So what I want to think about conceptually as is how quickly velocity is changing. Just like velocity was how quickly position is changing, this is taking it a step further and saying how quickly velocity is changing. If I'm going to write my acceleration equation here, I'm going to say acceleration is equal to delta v over delta t. Let me go ahead and box this because we really want to make sure we know this. So I have, once again, this is the acceleration. This is the change in velocity in meters per second. And as a reminder, this is the same thing as v minus v naught, the final minus the initial. That we could plug that in right there. And this is the change in time in seconds, which we could rewrite as t minus t naught. So if I wanted to, I could rewrite this equation as v minus v naught over t minus t naught. It's the exact same thing, but this is a more concise way of writing it out. Now let's talk though about what exactly the units of acceleration are going to be. Well, I have meters per second divided by seconds, so the units are really meters per second, which sounds a little awkward, but what we're saying is how many meters per second is the velocity changing each second. If I have 2 meters per second, what that's telling me is that the velocity is changing by 2 meters per second each second. However, physicists are lazy, and there is a little bit of an easier way to rewrite this, but I really want to emphasize that this is really what it conceptually means. This is a way to think about it, is that how many meters per second is the velocity changing each second. A different way we can write it, we can kind of do a little mathematical derivation here. So if I have 1 meter per second, I'm going to rewrite this slightly. I'm going to say I have 1 meter over 1 second, which is 1 meter per second, divided by, and now I'm going to make seconds into a fraction by just saying 1 second over 1. Remember that over 1, that just is the exact same thing. Well, if I divide one fraction by another, I can do the same thing by multiplying it by the reciprocal. So this would be 1 meter over 1 second times, I have 1 over 1 second, because I'm going to multiply by the reciprocal. And if I multiply this across, I get 1 meter over 1 second, but it's going to be 1 second squared. And this is often written as 1 meter per second squared. So this is a different way of writing the units. We say the acceleration is in units of meters per second squared. So that's how we say meters per second squared. But it's the exact same thing as meters per second. So often when we talk about accelerate, a real nice way to think about it is imagine you're driving your car. And there's probably one instantaneous way that we can accelerate for sure, and that would be to step on the gas pedal. Because if we step on the gas pedal, the car is going to speed up, right? That makes perfect sense. But remember, acceleration is any change in velocity with respect to time. So that's not the only way you can accelerate a car. In fact, there are 3 real key ways to do it. One is to hit the gas pedal and speed up. Another way, though, is to slow down. So if we hit the brake, and I think the brake's a little hard to see here, but if we hit the brake and slow down, we are changing the velocity, so that means we are still accelerating. So even if you brake, you're still accelerating. What about the third way? Well, remember, velocity has magnitude, a number, and direction. So if we're going at a constant magnitude, how could we change its velocity? We could change the direction of the car by turning the steering wheel. So there are actually 3 different ways to accelerate. 1, we can speed up by hitting the gas pedal. 2, we can slow down by braking. Or 3, we can change direction by using the steering wheel. All 3 of these count as acceleration. I know that's weird because in regular, everyday conversational English, when we say accelerate, we just mean this one. We only mean speed up. But in physics speak, we have 3 different ways. We need to be comfortable thinking about it. Now, before we take the next step, I want to have a brief pause and really mention something that might be new to you, which is that anytime we're in physics and we measure any sort of number, we have something called different measured quantities. So in all the labs we've done so far, like heights or times or velocities or speeds or whatever, they can all be grouped into 2 columns, essentially. The first one are what are called scalars. Scalars have magnitude, or in other words, they have a number or a quantity, an amount, but no direction. Okay, so what would be some examples of this? Well, the 2 obvious ones we've already done in class would be distance and speed. Some other examples would be like mass, for instance. We don't say that you have mass up or down, you just have mass. Another example, though, that's a really important one we want to add here is time. And that one might be a little surprising because you might be thinking, well, time moves forward, so doesn't time have a direction? But another way to help you think about it, there's no negative time. Time just goes one way, so there is no option of going in a different direction of time. The other option we have, the other type of measured quantity, are what are called vectors. And vectors have both magnitude and direction, and they have to have direction, which means really that they can be either positive or negative. So what are some examples of vectors that we've discussed so far? Would be displacement. We would also have velocity. And we're also going to have acceleration. And there are many others like force and momentum, and we'll learn them at a later point in time. But I really want to focus on this point here, that acceleration can be positive or negative. What exactly does that mean? Now, so you know, we're going to talk about scalars and vectors in much more detail in later units. All we need to know right now is that scalars, no direction, vectors, magnitude and direction. Well, since acceleration is a vector, it must have direction. But what does positive acceleration and negative acceleration mean? Okay, and this is where things get a little hard to remember. So first off, positive acceleration, you might think, okay, well that must mean speeding up, and negative acceleration must mean slowing down. That's not really accurate. This is not really the case. Instead, positive acceleration means v, or the velocity, is becoming more positive. Or in other words, the velocity is going to, like, positive infinity. And a negative acceleration, let me get the right color here, there we go, is really telling us that the velocity is becoming, there we go, more negative, or it is going to negative infinity. What exactly does that really mean? So it's just a reminder of what we learned a minute ago. The slope of a v versus t graph gives ACC, or the acceleration. So that means anything I get from the slope will tell me about the acceleration. Just like with a position versus time graph and velocity. It's the same sort of skill, but we're applying it in a slightly different context. So in other words, if I have a steep slope and a shallow slope, this acceleration must be bigger than this acceleration because this slope is bigger than that one. If I have a positive slope, that means I have a positive acceleration. If I have a negative slope, I have a negative acceleration. And if I have no slope, it's pretty much perfectly flat. I have no acceleration, and therefore this is at constant velocity. It's not speeding up or slowing down. But let's go back to a positive acceleration again. Let's say we start down here. Well, the slope never changes. So this is always a constant acceleration because the slope is constant. And additionally, it's always going to be positive. But what do these two different segments mean? Well, let's first look at this one. If I look from here to here, I am moving away from 0 and then going to a higher number in the positive direction. So a positive acceleration seems to be telling me that if I have a positive velocity, I'm speeding up. So this is the same thing as speeding up in the positive direction. But now let's look at this part down here. If I go from here to here, it's still a positive acceleration. But now I'm going from some number that is greater than 0 and then going to 0. So I'm actually slowing down in the negative. So now let me do the reverse. Let's start up here and have a constant negative slope. So we have a constant negative acceleration. Well, that tells me if I'm going from this point here to this point there, I am having a negative acceleration, and I'm starting at velocity 0 and going to a higher negative velocity, so I'm speeding up in the negative direction. But if I look at this part up here, I start at a higher positive velocity and move to 0. So negative acceleration is telling me I am slowing down in the positive direction. So what is this really telling us? We can break this down into two pretty key relationships. If the acceleration and the velocity are in the same direction, that means we are speeding up. Similarly, if I have acceleration and velocity in the opposite directions, so one is positive, one is negative, rather than being both positive or both negative, this means I am slowing down. So what are the big takeaways here for non-uniform v versus t graphs and acceleration? One, you want to be able to determine if an object is speeding up or slowing down from a v versus t graph. Is it moving away from the axis and speeding up, or towards the axis of the v versus t graph and slowing down? We want to be able to determine the acceleration of an object using the equation a is equal to delta v over delta t, or using it to find the slope of a v versus t graph. And lastly, we want to connect positive negative velocity and positive and negative acceleration to speeding up and slowing down. If they have the same sign, so if I have a positive velocity and a positive acceleration, that means I'm speeding up. Negative, negative, speeding up. If they have an opposite sign, so positive velocity and negative acceleration, or the other way around, it's slowing down.